nice to be here to meet many friends here. So next, I will talk about global mean sea level rise. In the recent decades, global mean sea level is rising at an accelerated rate. According to this Nature paper, ocean thermal expansion, ice mass loss, and changes in terrestrial water storage cause the global mean sea level rise. Before 1990, you can see here the rate of sea level rise remains below 3 millimeters per year, however, after it goes beyond. And compared to the beginning of the last century, today the global mean sea level is about 20 centimeters higher. According to IPCC report, at the end of this century, sea level will further rise about 28 to 55 centimeters under the 1.9 scenario, or about 63 to 101 centimeters under the 8.5 scenario. Sea level rise always attracts many attentions, in particular in coastal regions, since it brings coastal hazards and risks. However, on a global scale, it remains difficult to observe or investigate the climate impacts of sea level rise due to the low signal-noise ratio, because the recent sea level rise remains small in centimeters. IPCC report suggests that Paleo-Climate modeling provides a unique opportunity to investigate the impact of sea level rise. Since the report gives us several examples here, you can see the last interglacial period is a typical one. During the last interglacial period, sea level is about 5 to 10 meters higher than today. However, it is not easy to use climate model to simulate the climate impact. One example here you can see is the last glacial maximum, LGM. Due to the sea level drop, about 120 meters during the LGM compared to today, the difference in ocean volume should be 4 units here. However, you can see here we have 14 models, 8 of them do not consider or underestimate the change in ocean volume because it is not easy to change land sea mass in the model. And the models in the current generation cannot describe all process about the sea level rise. For example, atmosphere models generally assume that the ocean surface is flat under the atmosphere. However, there are variations in relative sea level. And climate models relies on model resolution. 1 degree model resolution is typically used in the global climate model. However, with such resolution, when the sea level rise is in centimeters, we cannot change land sea mass in the coastal region. And we should use freshwater input to increase the ocean volume to lift the sea level. But actually, in the model, we cannot do like this because ocean models have limited ability in simulating ocean volume change. So if we want to use the climate model in the current generation to simulate the impact of sea level rise, we need some special skills. These skills comes from the deep time modeling. We rise the sea level spatially uniformly. So we can add a number in the ocean bathymetry and reduce the same amount in the land topography. Although this experiment design remains idealized, but can capture the main features of sea level rise. So here we designed experiment in 3 groups. The first one is pre-industrial control run. Then in the second group, we carry out the last interglacial experiment. We consider orbital forcing and greenhouse gas levels. In addition, we consider sea level rise of 5 and 10 meters. In the third group, we carry out present-day experiments. You should notice here, for the present day experiment, we use atmosphere CO2 level 400, much higher than the last interglacial period. We know that there is a long-lasting problem in the last interglacial study, the model data mismatch, in particular in the southern hemisphere. You can see here, these points are reconstructed warming generally larger than 2 degrees. And here, the shaded color, the simulated warming in the southern hemisphere generally smaller than 2 degrees. So we use our model, Norwegian Earth System model, to carry out the last interglacial experiment. In this experiment, we only consider orbital forcing and greenhouse gas levels. Model generates cooling in the southern hemisphere. It is not surprising because the orbital forcing during the last interglacial period reduced insolation in the southern hemisphere, so model should generate cooling there. However, when we consider sea level rise of 5 meters and 10 meters, our model can generate strong warming in the mid-latitude of southern hemisphere. We need to understand why our model can generate warming in the southern hemisphere. We find the wind changes are the key. There are easterly anomalies in the mid-latitude of southern hemisphere. In the further step, we analyze the mechanism. So the sea level rise lowers topography and deepens bathymetry. Then we should see the adjustment in surface pressure, increase on land and decrease on ocean. This is reasonable because all of us have experiments for hiking. When we move down from a mountain, surface pressure increases. So surface pressure should be adjusted to sea level pressure. In this case, you can see positive anomalies around Antarctica. Following the wind theory, then the easterly anomalies should appear in the mid-latitude of southern hemisphere. Wind changes will lead to ocean feedback. We find an intensified southward ocean heat transport in the southern ocean. Thus, our model can generate strong warming in the southern hemisphere. However, we find that the model behavior is very different when we repeat the same experiment in the present day experiment. We also add sea level rise 10 meters here in the present day experiment. You can see the sea level rise lowers topography and deepens bathymetry. And we find the adjustment in surface pressure, increase on land, decrease on ocean. However, when adjusted to sea level pressure, this time you can see negative anomalies over Antarctica. That means we should get, following the wind theory, we should get westerly anomalies in the mid-latitude of southern hemisphere. That means intensified westerlies, which will cause cooling in most part of southern ocean. Why, with the same amount of sea level rise, one experiment gets warming, another one gets cooling? So we know that the response in surface temperature is due to the wind changes, and the wind changes follows adjustment in surface in pressure system. So, and we know that, surface pressure is sea level pressure is a function of surface pressure times a coefficient. This coefficient is a function of elevation and temperature. Then change in this coefficient is very, very small. So the surface pressure is the key. You can find the difference here with the same amount sea level rise. In this last interglacial case, the response in surface pressure is much larger than the response in the present day experiment. We should notice that the present day experiment use atmosphere CO2 level 400, much higher than the last interglacial experiment. That means the last interglacial experiment generally simulates a colder climate. In a colder climate, atmosphere density is higher. So that's with the same amount of reduce in topography will lead to large response in surface pressure. So our experiments are reasonable and convincing. Then we can, in next step, to use our experiment, try to provide some insight for our future. When we put these 6 experiments together, we do find some common features here. First, sea level rise cause a positive warming feedback. So with the sea level rise here, you can see there is an increasing trend in global mean surface air temperature on land. This increasing trend is significant, but here the increase here is very small. And then sea level rise causes a north-south temperature dipole in the Pacific side. Here you can see warming in the North Pacific, cooling in the Southern Ocean. Cooling here is caused by the intensified westerlies, and the warming in the North Pacific is due to the enhanced ocean heat transport in the North Pacific, according to our model. And you can see here, this dipole is evident even when sea level rise is only in centimeters, and this dipole strengthens with a further sea level rise. Next, sea level rise tends to weaken AMOC, but this response here is nonlinear. In our model, when we increase sea level, we find that the net water flux through the Bering Strait is increasing almost linearly. We should notice Pacific water is relatively fresher than the North Atlantic water. So this increased net water flux means there are more Pacific water inflow enters into the Arctic, potentially influencing the North Atlantic. So you can see here, when in our model, when the sea level rise is larger than 5 meters, this intensified Pacific water inflow largely reduces the sea surface salinity in the North Atlantic, thus reducing convection and deep water formation in this region. Thus, our model can generate a weakened AMOC. From our study, we demonstrate that a small global mean sea level rise, even in tens of centimeters, is large enough to generate significant global climate response, particularly at the mid and high latitudes. Although it remains early to answer, to prove that the recent global mean sea level rise already influence our global climate, but we should pay attention to that the Southern Ocean and the Bering Strait are the crucial region for detecting the impact of sea level rise in our future. At the end of my talk, I would like to use this slide to emphasize the importance of sea level drop in glacial climates. You can see here, this figure is not easy, but you can see there are 2 cycles here. This means work circulation on the Pacific side, the ascending branches, then descending branches. This is work circulation on the India side. And the blue color here shows a weakening of these ascending branches. That means sea level drop will cause the weakening of work circulation, potentially influence precipitation, maybe also influence the human disposal. Anyway, the take-home message for my talk includes these 2 points. First, considering global mean sea level change is important in modeling paleoclimate. Second, a slight, spatially uniform change in sea level is enough to modify atmosphere and ocean circulations. We should pay attention to these slow climate feedbacks that once happened in the past. For example, the sea level change, which will become outstanding in our future climate. That's my talk. Thanks for your attention.